about a situation where we have some kind of underlying distribution over all possible data points and over all possible target values. And this distribution is unknown to us, but it's there. And basically, all the analysis is done in a way that basically assumes that we are sort of sampling our examples from this distribution. Why is this important? Because this allows us to actually connect what happens in the training to what happens in the testing, right? Because before, I mean, if you don't put any other conditions on this, on what happens in the training and what happens in the testing, you have no, somebody can teach you machine learning and then on the exam can ask questions about polytology. Okay? So this distribution, which is there, is basically making sure that this doesn't happen. That you always have the same, that the world doesn't change on you when you, between training and before testing. Okay, and so we have assumed that the training set, which is composed of some T examples, so let's so this is training set capital T. And basically these T examples were sampled from this distribution independently. So each of them is chosen independently from the distribution. And then once we have the training set, we can do some training and select the function that's actually that we are going to use as our learner. So we have some hypothesis set and we choose the function that sort of optimizes, has best performance on this training set. That was the assumption. Okay, so we have some function which was trained on training set T, and we will denote this function h hat T. Okay? And I mean, so if you think about it, this function can be good or can be bad depending on how representative this set is, this training set, right? Because sometimes, extreme case, if you just have one training sample, right? It's very difficult to choose some good function just based on one training sample. So, but we also want to account for these cases. So this function can be very good or can be very bad. Can have a good training error, can have a bad training error. But there is also some function which we also don't know, but it's the best function from the hypothesis set, which is not best on this training set T, but best with respect to this to this distribution Pxy. Okay, so the best possible function from H, and we have denoted that as H star. And so now what we can do is we can write what we can expect from what's the connection between the testing error and training error and things like that. Well, not actual testing error, but the testing error, expected testing error, right? The one that if we go through the whole process, choosing the training set, then training the function, then choosing a testing example, and then evaluating. That's the whole thing. And if we do it infinitely many times, the expected testing error will be sort of average of all of these tries. Okay, so we can write it as, so this is expectation over one pair of x and y, which is the testing example, and expectation, I've said we also select the training examples, so expectation over training over the whole training set. And so we take our function that we have trained on this training set T and give it the testing sample X and compare it to the correct answer, which is Y. And we are working with just L2 norm. So this is the error of that particular function on that particular example, and this is saying this is expectation over all possible choices based with respect to this distribution. So this is expected testing error. And then we have sort of figured out last time that this can be decomposed into two parts. One is called bias, and this is basically something like this. So basically this is the expected error rate of the best ever function that we could get from our hypothesis set. Okay? And I mean, you cannot get any better. I mean, there is no way how you can get better, right? Because you would have to go outside your hypothesis space, which is not allowed. So this is called bias. And then we have a second part that basically says, yeah, but we are not getting anywhere close to this function necessarily. So we need to account for that. And this is expectation over all possible x's, expectation over all training sets. So we've got some trained function, that's our function that we are using, right? And it gives us different answers than the one that is that is the best. So basically, this part tells you how well you are doing with the training, with the size of the training set that you have chosen. And this is called variance. And as I was saying last time, these terms, bias and variance, as they are used here, are not the statistical bias and variance in any sense of the word. So please don't confuse the two, or don't try to match the two. Okay, and then we have also said, okay, we can actually decompose this term even further, this bias term, and we can relate it to a little bit surprisingly to the training error. So basically, this thing can be rewritten as expectation over all training sets 1 over T H T X I minus 1I squared. So basically, this is your training error on a particular training set, and this just says this is expectation over all possible training sets. Okay, so this is expected training error. And the second term here is something like this. So in some sense, this is a very similar term to this one, to the variance term, and it's called training variance. So the only difference that you see here is that instead of evaluating on some other sample, you are actually evaluating, you are asking what's the variance of the training error that you are getting with the number of samples that you get. Okay? So there is bias, variance, and bias can be decomposed into this. Any questions so far about these terms? So this is the kind of message that you should have gotten from the previous class. And the reason why we are doing all this math was that we wanted to draw two pictures. So I'm going to draw them again. So, and these are called like learning curves. Very nice name. Noble name. And so basically the first picture was, I mean, because what we can really do here is look at how, now we can look at how the training error, testing error, and the size of the training set, and complexity of the class, of the hypothesis class that we are selecting from is actually related. So this is what we are doing in this picture. So let's say that we fix the size of training set. So yes, of training set. Then we can draw a picture that has some kind of error in here, and then this is something that says like complexity of H. As I was saying, you can imagine that this is somehow related to what kind of hypothesis classes you are selecting. And one possibility is you can imagine, for example, that you have generalized linear regression, and that you have increasing, like linear function, quadratic function, cubic functions, and so on. That might be one possibility. But there are like countless other possibilities of getting a nested set of hypothesis classes, depending on exact learning setup that you are working with. And so we had this bias, and we said that the bias will basically go down. The question was why? Why the bias goes down? Yeah, so there is some function that has that is the best function possible. It might not be actually might not account for all the information that is in the probability distribution. And as you increase the size of the hypothesis set, you basically can get only better, right? You can get only closer to that one. So this is bias. And we had this variance term, and that's somehow increased. And why did it increase? At least in some. Well, we have a fixed training set, yeah? Yes.
As you only have a fixed amount of information you have training on, but to choose a function you need increasingly more and more information.
Yes, so if you have, so basically the idea is that if you have a more complex hypothesis class, you actually need more information to train at the same level, to choose the right function at the same level as before. And so this error, if we fix the size of the training set, so we don't allow you more information, then this will go up as you increase the size of the hypothesis. And so if you sum these two things, you get the expected testing error. Let's get some color here. So you get something like this. So this is expected testing error. And so you can see that it's not best choice to actually, take as complex class of hypotheses as possible, or if somebody says to you, yeah, complex hypothesis classes are not good, then you would choose like the least complex one, and that's also not a good idea. So there is some kind of good point where there is a good trade-off between bias and variance, and that's what you are looking when you are trying to set up a learning system. And we have said that on the left, this is called underfitting, and on the right, this is called overfitting. Okay, any questions about this? The other picture that we had last time was about, so before we had a fixed set of fixed training set, now we have fixed hypothesis class. Okay, so fixed class H. Again, we can, have error here, and here we will change the size of the training set. Okay, so now we are allowed we fix the hypothesis size, and now we are allowed to change to add more training examples. So what happens? So this is small t. So what happens here? First of all, we can look at this bias. What will be the line corresponding to the bias? It will be constant because it doesn't have anything to do with the training set, right? So, it only has to do something with the hypothesis class H. So it won't change with the changing training set, so there will be some kind of bias. There will be bias here. And then there will be, if you look at obviously, if you add some variance, the variance is decreasing with the number of examples. At least if you set up the learning system correctly. So if you add the variance to the bias, you get expected test error, okay? And so this difference actually decreases with the size. So this expected testing error will go something like this. Expected test error. And so this thing is variance. Okay? And so now if you look at this second part of this formula, so here you have expected training error and you have training variance. Again, this training variance with the number of training examples will decrease. So training variance plus the expected testing error should also give you the bias. Okay? So then you have something like this. Then you start somewhere here, and the training variance which is this thing, the difference between these two, will actually decrease with the increasing t. And this is expected training error. So basically, what this figure tells you is that if you increase the size of the training set, what should happen is you should, perhaps a little surprisingly, you are choosing better and better. You are choosing the better and better functions, most likely, with the increasing training set, right? But your training error actually goes up. And this is expected. This is something that should be there. So large training error is a good thing, in some sense. And then you start with a huge difference between this small number of training examples. You start with huge difference between performance on the training part, because it's the training error is low, testing error is high. As you increase this the size of the training set, the training error and testing error will get closer and closer together. If the things go right, they actually converge to the same value, which is bias. Okay. Any questions about this? Yeah?
I have a question about increasing variance or the increasing complexity of the hypothesis set. Is that like a provable mathematical thing, or is this just something that usually happens?
It is a provable mathematical thing, but we didn't prove it in this class. So yes, this is something that there is lots of things that we waved hands over because we didn't want to spend the whole semester on this. Any other questions? And also some assumptions must be met. That's also part of the deal, which we also didn't talk about. Any other questions? Okay, so the first question that we are going to look at today is how actually, what does it tell us? How can we deal with all of this in practice? What does it tell us to, what can we, I mean, this is a nice theory, right? But this is full of, expected this, expected that, which is computed over infinitely many choices of training sets and things like that. And you really don't know, you can't really tell, what is exactly expected training error, expected testing error, although you will try to do something on one of the homeworks later in some very simple scenario. But generally, the question is what this theory can actually give us to work with in practice. So how to deal with all this? How to deal with bias, variance, trade-off. And so ideally, some kind of estimation of training error you can actually get, right? It's just the training error that you observe on data, but you would really like to know to have some estimation of testing error or something. And and you would like to adjust your algorithms to actually take this somehow into account. I mean, I still didn't answer the question. So if you give me some particular problem, is it better to use quadratic function or I don't know polynomials of degree 5, right? And so the first answer to this, from the practical point of view, is something called regularization. And so if you remember, we had something, so we had a function j that was dependent on a set of parameters theta of your function. This is, now we are talking big about linear regression. That was basically measuring error, right? So this was something like 1 over t, sum over all training samples, h theta xi minus yi squared, right? That was our thing. And so depending on the class of the variables, you choose the best values of theta. So one way you can sort of try to get with your learning system to this point is to go and try to add something like some term that sort of gives you models for more complex hypotheses. Okay, so you have something some penalty, right? That depends on the parameters theta. So you can imagine it that you can even decide I'm going to use any combination of any polynomial function, any degree. But if I use 10th degree polynomial, I will actually get the high penalty here. Okay, and then you sort of don't have to decide because this function, this penalty function, will sort of take over. And once you are using the hypotheses that are too complex, then you are then this function is going to dominate, and then this part of the function is going to dominate, and it doesn't matter that you get low training error because you will never choose these things. Okay, so this is actually something that is so this is penalty for complexity of the complexity of chosen hypothesis. And basically this should roughly correspond to variance estimate. Which is still not that helpful because, I mean, how we are going to estimate variance, which is really like lots of, lots of stuff in there. And lots of expected values, right? Well, we don't like expected values because this means that we know something about the whole universe, about the whole function pxy. If we can compute that, then we don't need machine learning at all. We have the full information. Okay. And so for linear regression, there are some practical solution that has been developed. Some assumptions that we are working with right now. So first of all, normalize all xi's. So that means that every feature, that there are no features that have that are very large compared to other ones. Okay, so we assume that sort of, let's say, all the features have mean, all of the features have mean 0 and standard deviation 1 or something like that. Okay, so that's necessary for these things to work. So we will have mean 0 and variance 1. That really means like getting a large enough training set and then saying, okay, so let's compute the mean and variance, subtract mean, divide by variance, everything, and then remember and do it also during testing. Use the same values, not the new ones. Okay. So this is nothing that is somehow weird, or it's not even important, right? From the point of linear regression, it doesn't matter what's the scale of all these attributes because we just use different parameters. We want to use, like, if you decrease the value of something 10 times, you just use 10 times bigger coefficient, and that's it. So it doesn't change the task in any way, the normalization. But it's a good practice, and we actually need this because now what happens is the size of the coefficients let's say ith coefficient sort of tell us something about how important that particular feature is. Okay? Important particular feature is. So if after such normalization, you have some features that have a really small coefficient, then you may even forget about them because they only change the result very little, right? So in the end, you actually don't care because the change actually, the change actually doesn't change the target value that you predict in any reasonable way. So, and so there is a method called ridge regression that actually capitalizes on this idea that the importance of these individual features is actually somehow related to the size of the coefficient now. And basically, it says let's try to penalize large coefficients because they make sort of things unstable. Okay, small change. If you make small change in a particular feature, like introduce a little bit of noise, we have a very large coefficient. Then you sort of introduce a big change in the target value, and you may not want that. So let's see how this works. So basically, you say your j theta, that's the error function, is 1 over p. So this stays the same as before. And we add the penalty term, that is lambda times sum of squares of all coefficients. Okay, lambda is some kind of weighing constant. And probably we want lambda greater than 0. So this just penalizes the large. It likes to see lots of zeros. Okay? So the question is, if you take this error function, how do you actually remember? We had these normal equations or other optimization functions that could, other optimization methods that could actually help us to find the correct set of parameters theta. So the question is, how does this change? And in this case, this is a nice method because it doesn't change much. What happens is that you, instead of having, before we had x transpose times x times theta. So these were normal equation. Basically, we're looking for, you set up these n-linear equations. So this is basically, do you remember, does everybody remember this? What's the design metrics and things like that? Okay, so it has this design, you have this design matrix, you have this target vector. So this is basically a vector of constants. This is some kind of weights in a linear combinations for, and this is basically a set of linear equation, n-linear equation with n unknowns, where these are n unknowns. So if you use this particular function and you would go over all of this, computation again, you would get slight change, where you would also add here a factor I is the identity matrix. So basically, you would get one matrix that is, and lambda is just a number. So you get one matrix that has diagonal lambdas on it, and that's it. And if you don't believe me, you can just go over the derivation and see it by yourself. Okay? So if you have this rich regression, if you have this type of penalty, you can just, go and modify a little bit your system of linear equations, and now you have now you can derive the best set of parameters with respect to this error function. So another way, which is slightly better, actually. So actually, I was lying when I was saying this favors lots of zeros. This doesn't favor lots of zeros, right? Because if you have two correlated features, if you can actually split this into between the two correlated features, you get a better value. So we'll use actually more features. So we would like to fix that somehow. And so how people decided to fix this is called by a method called lasso. So this is least absolute shrinkage and selection operator. No idea why this is called that way. I won't even write it down. So everybody knows this as a lasso. And basically the only change is that instead of using, squares of the parameters, you simply use absolute values. So this is actually something that will give you lots of zeros in the, it's at least indifferent to the correlated variables. Yeah.
Can I have a question? In the next sum, there's a t. In the equation before it's n.
Yeah, this should be n. Thank you. Okay, so let me rephrase. In here, what happens if you have two correlated but not really the same variables? You are likely to split the things between the two. Because even though you introduce additional error, like one is better to use than the other one, okay? But splitting this error splitting this squared error between the two is actually very profitable, right? While here, this doesn't happen, so the variable that is best correlated with the result actually wins, and all of the others are likely to be zero. Of course, if you have perfectly like the copies of the same same feature again like 10 times, then it doesn't work. But in general, if you have something, one of them has is the best to use, and you use that one. Okay. So this will create lots of zeros. Lots of zero parameters, which basically gives you this desired effect. I don't want to use too many parameters because that makes more complex hypotheses. Yeah?
What do you mean by zero? Is it like actually the exact zero?
Exact zero.
Or, okay.
It doesn't make sense to sort of dwell on small differences, let's say. So it doesn't make sense to create something that is 0.0001 because that would get penalized, and also as I said, if you have like variables that are correlated, then the best is chosen, most likely the best is chosen, and all others will be zero. So you're basically doing this simplification of the feature space. Okay, unfortunately, this doesn't have such nice solution as this one. So you would use some kind of numerical optimization, like a gradient descent or something like that, to actually get the. So numerical optimization is the answer here. No closed form solution. Which is not, since most of the time you will see it in one of the assignments, one of the practical tutorials, that actually numerical optimization is usually preferable to the exact solution, which might be a little bit surprising to many of you. So it's not. It's like a aesthetic problem, but it's not a big problem in practice. Okay, so these are the two standard regularization options for linear regression. Any questions? Okay, so the second thing that people are trying to do, if they can't think of good regularization options, they actually try to do something called holdout testing, which is also built on this idea that we somehow need to figure out what's the difference between training and testing error. okay? Or in the particular setting that we are working in. And the idea is that we will, instead of using the whole training set for the purpose of training, we'll actually set some part of the training set apart to actually do this evaluation. So the idea is, okay, take, I don't know, 4/5 of the training data, use them for training, and then use 1/5 of the training data to actually use the estimation of to estimate the error, the difference between training and the testing error. Okay? So part of the training data set aside for estimate of the testing error. So what's the problem with that?
Well, you don't know how to split the training data to be representative of the
Well, you sort of know, because training data, you assume that they are independent samples. So if you do independent samples of independent samples, you get independent samples. So what portion of the training data I would set aside for this particular thing? 1/3, 2/3, 1/5, 4/5. So who would say less than half? Okay, who would say more than half? Okay, so why did you say less than half? Yeah, whoever said less than half. Okay, good. Any other reason? Why would you set less than half? No reason at all. Everybody does that. That's a good reason. Everybody jumps off the cliff. Let's do this as well. Okay, so why you might not want to do it? Because so if you take a little data for the estimation of the testing error, variance of that estimation will be actually quite high, right? Because if you estimate the testing error just on one sample in the extreme, that's actually not a good idea, right? Because the testing error might actually vary quite a lot among the different samples. So actually, the more data you have for estimating testing error, the better the situation might actually be, right? The better estimate of the testing error you actually get. So it might actually make sense to choose the more than half of the data as a testing data, as this evaluation set. So that is not a good idea.
If you use more than half for testing, it can actually become already training data if you use more of the time.
I didn't understand that.
Data and the testing data may be changed.
Yeah, but this doesn't. So this is also called something like this. This data set is also called validation set. Often. Okay. So yes, that's true that I might. So basically, how I would use all this, maybe I can specify a little bit more. So I would train my system, estimate the error, and see how big is the error. Now I can change the hypothesis space, use the same training data, and estimate testing error again, and try to see, where in this thing I am. Okay. what's the best, or where what's the best what's the best way to adjust? What's the best testing error that I get in the end for which hypothesis, for which hypothesis space? Because if I take the too complex one, then it's going to be the estimate of the testing error is going to be high. If I take too simple, it will also be high. So I can actually optimize my set of hypotheses on that. Yeah?
After you choose your best set of hypotheses, are you going to use your whole training data to train a final model?
Yes, I can do that, but so if I take the very large portion of the data for very validation set, I'm actually very much shifting in the direction in here, right? Because if I'm losing like 1/3 of the data for training, then it's suddenly a different learning system, right? It's completely. I mean, it only estimates. It only makes the estimate based on the 1/3 of training data. So you really would like to use like most of the training data for your training and only for validation. But then if you do that, then you get imprecise validation error. So maybe the error that you will get is high. It's a chicken and egg question sort of. So if you use a large validation set, it's wrong. If you use small validation set, it's wrong. So the question is how to escape from that. And there is a procedure that is actually very easy to do. And that can actually avoid most of these problems. The idea is that we split training set into, let's say, some k sets T1, T2, and Tk. So each of these is equal sized. Okay? And now repeat for all I from 1 to k. And idea is use all tj except for those that are not I. So everything else except for ti use for training. And compute error based on just ti. So that sort of gives you a precise set of errors, but you repeat that. So you repeat that for first set, second set, third set, and so on, as a holdout, and then you average. So get the final estimate on as average of all cases. So at some point you have used all of these data sets you have used as trainings, and all of them you have used as testing for estimation. And then you can, this gives you better estimation of the. This gives you a reasonable estimation of the error because you didn't use just 1 point or a few points to estimate it. You actually used the whole data set, everything that you had for estimation of the error. And since you split this to many, like 10 parts, you always use 9/10 in every single instance. You use 9/10 of your training data for training. So it's not as different from the whole set that you have. And then you probably, after you choose, your settings, what degree of polynomials you want to use or whatever. After you do this, then you actually retrain on the whole training set. Yeah.
One question that you use for training also your validation data, but somebody can say, okay, but you don't know how it will behave in the real world because you already use training validation data for training. So
yes, and then I have an answer for you. Set aside another validation set. Okay? So this is the procedure that helps you to select the right right hypothesis, correct size of hypothesis space. Whether you use simpler hypothesis or more complex hypothesis. Yes? Actually, that's a good question. So let me just finish this. This is called holdout testing. And actually, I mean, anyway, usually the number is 10. So it's called tenfold evaluation.
Just because we have 10 fingers.
Yeah, just because we have 10 fingers. But there is also a method that is called leave one out. Which is sort of taken this method into absurd ways because it splits everything into training sets or into sets of size 1. So basically, you always just hold out one example, train on everything else, evaluate on that example, and then you cyclically rotate. And that actually gives you the best estimates. Why it's not used more often, if you have lots of training examples, it actually takes lots of time. Because you have to repeat training procedure for every training example. So anyways, so this tells you why estimating testing error aside from independent samples, from samples that are independent of the training set is important. And these strategies tells you how to actually estimate testing error. Any question before we go any further? So the sort of good best practice or best practices for this, good best practices. So if I have a data set, training data set, I usually right at the beginning split it into training set, validation set, maybe another testing set if I need to test a few different strategies on something. So validation set is training set is just for training. Validation set is for playing with the parameters, size of the hypothesis space, and other things. Testing set is for final evaluation. You don't touch it until you write the final report or whatever. Okay, and you must ensure that all of these three sets actually have a similar characteristics, so that they are as close as possible to independent samples from distribution of all possible samples that you can ever get. So that's really important, because once you get different properties of testing set compared to training set, you are screwed. Okay, and another thing that you should take into your heart, if the training goes really well, and if you get really, really low training error, usually that means that something is really, really wrong. Okay? So high training errors are sort of your friends and not your enemies. Okay. So that's for this part.